Hi, I'm Charles McFarlane, Chief Business Officer for CodePlay Software. In this presentation, I will begin exploring the scope and the complexity of these distributed and federated data streams and how open standards and industry-adopted software like SYCL and OpenCL from Kronos are already enabling all types of computer architectures in other markets and equally apply to automotive. The talk will outline the requirements of the processing the data in the car, on the edge, in the cloud, and in data centers and then back. There are three main takeaways from this presentation. Autonomous vehicles will generate massive amounts of data and require massive amounts of processing. The second thing is the system built for these data centers and processing to work together via industry-approved programming standards. And then third, through open standards, systems can be built today that will enable future improvements and reduce costs. So the challenge is, how do we integrate and validate all of these data sources? LiDAR, ultrasound, radar, camera data, and that can be driver camera, outside cameras, vehicle monitoring data, and offline locally stored mapping data. You're bringing together all these sources of data and you've got to merge them all together. So huge quantities of data, varying types of data, and requiring different types of processing required. So with all these different sources of data requiring different types of processing, how do we integrate it and validate it and then process the volumes of data that are required with different algorithms and different processing architectures? Fuse it all together, extract the necessary data to make sense of it all. How do you manage all of that? That is a really, really tough challenge. So how do we manage this software challenge? Well, we've mentioned before the huge quantities of data, but there's huge quantities of software, the latest software techniques, amount of software that's already pre-existing, new stuff that comes along, and the whole development platform, the problem of large-scale software development programs. For maintaining the software, as new sensors and processors become available, regional legislation, improvements in the algorithms, bug fixing is always going to be an update to your software for the lifetime of the vehicle, perhaps 20 years from now. There's achieving huge performance. It's no good in having inefficient algorithms at high-level program. You have to get the highest performance out of that. Processing the increasing volumes of data, achieve faster throughput, faster real-time performance. You've got to validate the software. Because it's automotive, functional safety, you need well-validated systems to make it safe. And embrace new accelerators and processors such as GPUs, FPGAs, or dedicated processors. All these 5 challenges result in a huge task. So how is this manageable? So processing and achieving performance is evolving and the challenge is changing. Today, the latest semiconductor nodes and architectures, the speed of computation is around 1 nanosecond or so. But the bigger problem is about moving data. On chip is fast, maybe 10 nanoseconds. Off chip to SRAM, perhaps a microsecond, to another processor, say 100 microseconds. A few years ago, it was about the speed of computation to achieve performance. Today, it's more about moving that data. So combining kernels and limiting data movement is key to achieving performance. And this is especially true within automotive and the diversity of many sensors around the car. Much, much more than computation for performance. So for high performance system designs many different edge processors on different chips and probably using different software languages. As the market evolves, the standalone and the edge of car solutions are an obvious architecture. This results in slow communication channel and especially when trying to fuse all this data together. So this is an attraction to a big chip with huge amounts of compute. Keep data on chip for faster access and lower power consumption, perhaps with some duplication to provide some functional safety. So looking at the system in the chip, one big chip with different types of processors and accelerators. This allows the right type of processors to be used for specific algorithms when processing a specific stream for a sensor. The familiar CPU, GPU, specialist deep learning algorithm and accelerators with the DSPs, giving a broad processing capability depending on the algorithms and function needed. This is how it works in many other markets, such as smartphones, where they're handling many different features and sensors. In automotive, we're seeing this combining, even devices needing deep learning, both low precision accelerators and high precision with GPUs are required. It's a very complex and heterogeneous environment that's needed, but keep it on a single chip. With all the different algorithms and functions needed and combining different multiple streams per function, the challenge is bringing multiple data loads to the processor to ensure data is not being moved between processors multiple times. The solution is to take the processing to the data and not the data to the processor. It avoids data movement. This avoids a massive overhead involved in moving data around the system. Migrating code between cores is a major part of this approach. This is not always true. Sometimes there may be situations of moving data to the processor. This type of balancing is important to achieve maximum performance. You don't know the size and the types of data before you do it. These calculations dominate the performance, and you won't know this in advance. So how is it possible? So if we look at modern programming models for these systems, you have a common programming model. Mostly today, they're based on C++ for inference and actually for driving the car. But Python is also there. It's also used in data centers and deep learning. They use Python quite a lot. And you'll probably use this for training the systems in a car. You also get a tuning layer. For each core, you can write the code once and then tune it for each core, which is extensively, it can be done automatically. It's used a lot, it's not magic, there are caveats around this, but auto-tuning helps a lot to achieve performance. And this can be adapted across many processors and accelerators. The common programming model allows the algorithm and functions to be written once and then tuned to the different processors. So this is where standardization comes in. So how do we enable code to run across multiple processors and still be maintainable? There's this stack of well-defined and specified software techniques from top to bottom. This absolutely does not mean adding processing overhead, and in fact, that often the opposite. It actually saves you performance and gains you some performance. So from the bottom, you always need a low-level instruction set. And here we're showing RISC-V as an example. This is a processor specific. You will always need a low-level hardware access, and here we show the standard ones. How to send instructions to the processor, such as to allocate shareable data, etc. A portable instruction set is required, which will not be compiled in a car at runtime. It allows the compilation stack to work. Here we've shown a standard one called SPIR-V. It works the same way as the compiler works. SPIR-V, VINA is a Kronos open standard specified standard there. Languages shown as SYCL and OpenCL, again, open standards from Kronos, allowing high levels of performance. Libraries and models that are optimized for each processor, such as one API shown here, was started by Intel, but now also supported by us, by CodePlay. So from top to bottom, you achieve high level of performance. Each layer is well defined and specified. This is really important for automotive so that verification and validation is done against the specification and can benefit from third-party tools for full qualification. How do we do the tuning? Well, it's a well-understood problem now. We break all of the operations down into a manageable set of classes of operation, for example, automotive, climate, or genetics. Each area has its own popular set of operations. There are not really that many classes of operations. We can generalize it and create a template implementation for each generic operation. Then optimize this for each processor. So you don't optimize every operation for every processor. We optimize the generic class of operation. This is a much reduced problem, and do it in a way that is tunable. Then apply the right hand optimized template for each operation to each processor. This is a real world technique. It's used in supercomputers and data centers for AI today. You're not sacrificing performance, but managing to build a large and complex compute system needed for automotive. So to achieve this in the real world, here are some examples to show the supercomputers in America. They use SYCL industry standards supporting all major GPUs, providing cross-platform portability. Over 10 million lines of code converted already, showing the maturity of the tools and the closeness of the language to CUDA, and maintaining highest performance without loss to this architecture, actually gaining performance when abstracting and compiling at a higher level. Portability between hardware, the rapid software development, and the porting phase, and ultimate performance. These are the major needs of compute systems. For automotive, we're working with people like Renesas, NSI Texi, Imagination, and Intel. The technology is valid from supercomputing, cloud AI, and automotive. It is adaptable. So what's the benefits of this approach? Well, you've got performance. Remember, it's about taking the processing to the data, avoid the data movement, which is the biggest cost to these systems. And as validation provides a big gain, every component has a specification to test each component against a widely, well-defined and adopted open standard for others to support. It builds up a third-party ecosystem for others to validate against. Huge amounts of productivity. Many people are out there and have already done the requirements and the tools already. So they're already out there and ready to do that job. The long-term maintenance is achievable because standards have a long life. They're defined by the industry and will not be redundant in a few years. This is a huge, and it's a huge item, and it touches on, for example, there's the UNECU, the Working Package 29, which calls on software to be maintainable for the lifetime of the vehicle, especially for security. This means maintaining software for 15 to 20 years. That is an impossible burden if programming in a proprietary programming language. Multiple suppliers is critical to OEMs, meaning portability between hardware solutions is essential. Using open standards for programming gives that portability and opens up the supply chain. Most research and advanced development is done in C++ and standards-based programming platforms. So embracing the latest technologies becomes much easier and much quicker to evaluate and, of course, into production. Being based on modern C++, the availability of skills and the speed of adoption is much better. There's already an established ecosystem of documents, samples, training. It's all out there, it's available to ensure a rapid adoption of open standards. So putting this into practice, this is what we do at CodePlay. Lots of different hardware already enabled, and our products enabling these standards are available to be used in automotive compute systems for ADAS. Our product, Akaran, provides overall platform with benchmarks, with test suites, ecosystems, libraries, and the frameworks essential to bring a reliable product to market. Compute CPP is our closed source implementation of the SYCL open standard. We led this standard and created our own product providing performance and portability. Compute Orta is at the heart of the system, providing OpenCL and Vulkan. Both of these are open standards again, and easily ports to new hardware, providing a foundation platform based on well-adopted open standards. We also support many open source projects. They work together and provide extensive interoperability across multiple platforms. So that's it. This is a one-slider about CodePlay. We're based up in Edinburgh. We've been around for almost 20 years now, getting on around 80 odd people, mostly engineering. We've got our products there, Akaran, which is the umbrella product, which covers all the benchmarking and frameworks and ecosystem. Compute Orta is our closed source SYCL implementation, and Compute Orta at the heart, which gives you the OpenCL Vulkan implementation. You can see we've worked with many of the global big companies out there, and there's more in there that I cannot mention. And market-wise, as well as automotive or into HPC, basically anything from supercomputers right the way down, including automotive, is covered by SYCL and Compute Orta with our OpenCL standard. And technologies, if I move slightly to the side here, then it's artificial intelligence, machine learning, vision processing. Okay. All right. I hope you've enjoyed the presentation, and yeah, reach out to CodePlay for any questions.